student, welcome to all of you in the next physics session. Now we have to start here the chapter number 5, oscillation. This is the video number 32, and this very important chapter, oscillation. In that chapter we have to see here the linear simple harmonic motion, the differential equation of linear SHM, expression for acceleration, velocity and displacement. Then this graphical representation, this part should be the reduced in that chapter. And also last point, that the damped oscillation, free oscillation, that part is also reduced. Then composition of SHM, then energy of particle of SHM, simple pendulum and angular SHM. This part we have to see in that chapter number 5, that is the oscillation. This is a pure mathematically derived chapter, this oscillation. In this chapter, first we have to see here the introduction about the what is meant by the vibratory or the oscillatory motion. Oscillatory disturbances traveling through the medium without change of form, it is known as a wave or the wave motion. And in this vibratory or the oscillatory motion, the particles are the to and fro from its mean position. And so that these examples of these oscillatory motions, which are the rocking of the cradle, the motion of the pendulum of a clock, then vibration of guitar or violin string, also the up and down motion of the needle of sewing machine, and also the oscillation of the spring. These are the examples of the oscillatory or the vibratory motion. Then we have to see the next terms, the what is meant by the periodic motion, because we have to see the linear simple harmonic motion. Then we have to use this word, it is a linear periodic motion of a body. Then what is meant by the periodic motion? The periodic motion is a motion which repeats itself in equal intervals of the time. Motion in which repeats itself in equal intervals of the time. This is nothing but periodic motion. And a body performing the periodic motion goes on repeating the same of this movement, and the time taken for the such state of the movement, which is called as a period or the periodic time. And these examples of this periodic motion, we know that these are the examples of that periodic motion. This is the introduction about that this chapter, oscillation. Now we have to see here the first point, that is nothing but the linear simple harmonic motion. There are the two types, linear and the angular. Simply this meaning of that linear is along a straight line. This is nothing but the simple harmonic motion. Then we have to see here what is meant by the linear SHM. In short, this simple harmonic motion is nothing but the SHM. In this chapter we have to write in short form the simple harmonic motion, SHM. Linear SHM. Linear simple harmonic motion is defined as, it is a linear periodic motion. We have to give the explanation about this linear periodic motion. Therefore, it is a linear periodic motion of a body in which the body should be always directed towards its mean position, and the magnitude of the force is directly proportional to its displacement from the mean position. This is nothing but the linear SHM. Remember these terms, linear SHM. For that purpose, we have to give the examples of the simple pendulum. If you have to take the examples of this pendulum pulled on one side and release it, then it can be moves on two sides from its mean position and oscillating to and fro from its mean position. This is nothing but the linear periodic motion, and we have to say that this pendulum performs the linear SHM, because in this simple pendulum, this pendulum which can be directed towards its mean position, and magnitude of the force which is directly proportional to the displacement, and so that this pendulum performs the SHM. This we see here the example of this linear SHM. Now we have to see here, derive the differential equation of linear SHM. We have to ask even your board like this question. Define the linear SHM and derive the differential equation of linear SHM. Then we have to write the first definition, linear SHM, and then derive the differential equation of linear SHM. First, we have to see here, for differential this equation of linear SHM, we have to satisfy the following two conditions, and this is nothing but the definition of the linear SHM. Particles performing the linear SHM, then and then these particles should be satisfied the following two conditions. That conditions are, the body should be directed towards its mean position, and the magnitude of the force is directly proportional to its displacement. If these two conditions are satisfied, then this particles performs the linear SHM. In that chapter, you have to remember that if these two conditions are satisfied, then this body should be performs the linear SHM. What is these two conditions? First condition is that the body should be always directed towards its mean position, and magnitude of the force is directly proportional to its displacement from its mean position. We have to give here the examples of the pendulum. We have to remember this example, then you can understand what is meant by the linear SHM. Now, these two conditions can be written in a mathematical form as follows. That is, this force is directly proportional to displacement, so that we can write here F is directly proportional to x, and therefore F is equal to minus kx. Proportionality sign we have to remove here. Take the constant k, that k is the force constant, and negative sign indicates that this force and displacement are opposite to each other. Again, remember this example of the pendulum. If you have to pull that pendulum, then which can be the moves in opposite direction, so that this force and displacement are opposite, so that these negative signs are here. Now, this is the equation number 1, F is equal to minus kx. Now, this velocity of the particles in differentiation form, we can write here, this velocity is nothing but the rate of change of displacement with respect to time. Therefore, we can write V is equal to dx upon dt. That is the d by dt of x. Okay. Also, we know that the acceleration of the particle, which is given by a is equal to d by dt of v, that is the rate of change of velocity with respect to time. A is equal to dv upon dt. Then we know that this v, that is the d by dt of v, but we know that this v is nothing but what? Velocity, that is the dx upon dt, and substituting this value of v dx by dt in that equation dv by dt. Therefore, A is equal to d by dt of v, and instead of v, we can write dx upon dt. Therefore, d by dt of dx by dt, we can write d2x upon dt square. In physics, we have to say here not d square, but we can say here the d2x upon dt is 2 times, therefore dt square. Here only d is double, therefore d2x upon dt square. This is the equation. This is the in the differential form of acceleration. Now we know that if m is the mass of the particles, then this force acting on that particle, which is given by F is equal to ma. This is the very basic form. We know that F is equal to ma, that is the mass into acceleration. And then we can substitute the value of a, that is the equation number 2, in this equation number 3. Then F is equal to m. Instead of a, we can write d2x upon dt square, and therefore we get this value of F is equal to m into, instead of a, we can write here d2x upon dt square. This is the equation number 4. We obtained here the equation number 4, F is equal to m, that is the mass, and acceleration a, we can write d2x upon dt square. Now we can see here the equation number first, F is equal to minus kx, and equation number 4, F is equal to m into d2x by dt square. Then compare the RHS, because the LHS is same. Therefore, compare the equation 1 and 4. We can write first here m d2x by dt square and is equal to minus kx. This minus term take this side. then m into d2x by dt square plus kx is equal to 0. This is the equation number 5, and above equation is known as the differential equation of linear SHM. M d2x by dt square plus kx is equal to 0. This equation number 5 is called as the differential equation of linear SHM. This is very, very important. And from this equation, we can derive the three expression for acceleration, velocity, and displacement. And all these formulas we can use in the solving these numericals. First, we have to say here the acceleration. To solve this formula for the acceleration, we know that the differential equation of linear SHM. If you have to write here for find out this formula for the acceleration, we know that this differential equation of linear SHM is given by m d2x by dt square plus kx is equal to 0. We can write here m d2x by dt square plus kx is equal to 0. We have to find out the only acceleration. The d2x by dt square is nothing but the acceleration in differential form. So that here is m is not there. So that to remove this m, we can dividing throughout by this equation m. We can divide by m throughout this equation. Then m is cancelled. Only remaining term is d2x by dt square. Dividing m, k by m into x is equal to 0. 0 upon m also 0. Then we can put here like this k by m is nothing but the omega square, angular frequency. K by m is equal to omega square. Substituting this value, instead of k by m omega square, we can write here d2x upon dt square plus omega square x is equal to 0. But we have to find out the acceleration, so that this term is remain as it is, LHS, d2x by dt square, and this plus omega square x, take this right side, and this is nothing but the minus omega square x. Therefore, the d2x by dt square is equal to minus omega square x. This is the equation number 6, and this d2x by dt square is nothing but, this is the acceleration, and therefore formula for the acceleration is nothing but minus omega square x. Very, very important. Acceleration, that is d2x by dt square is equal to minus omega square x. Okay, you don't understand? Then we have to find out the expression for the velocity and displacement in next video. Okay, thank you.